In 3.2, we're going to be talking about the relationship between a function, a first derivative, and a second derivative, but we're going to be focusing on the graphical representation of those graphs. So if we're given the graph of a function, what does that tell us about the derivative? If we're given the graph of the first derivative, what does that tell us about the function? And what does that tell us about the second derivative? And how do those graphs relate in a way that could help us identify or recreate a graph given one of those three graphs? So that's really the focus of today. So if you're given a graph of a function, how can you determine approximate values of the derivative? Well, the derivative is the slope of a tangent line, which means that we could look at the slope. So here we are in this first example. We're given the graph of f on the left, and we're being asked to sketch the graph of the derivative on the right. So when we're given the graph of f to graph the derivative, we want to look at the slopes and estimate the slopes, and we're going to start by plotting those as points. So if we look right here at -4, this slope looks like it is approximately 2. If I was having a tangent line that was tangent at the point -4, thinking that this function would continue, it looks like that derivative would be, that slope or derivative would be about 2. Looking up here, right around here, and I know that's not touching, but this slope looks like it would be about 0. Looking over here, this slope looks like it would be about 1. Looking down here, it looks like it would be 0 again. And then looking over here at +4, this slope again kind of looks like it would be 2. So what did I just do? I looked at key values or key parts of the function itself and identified the slope at those values. So I said, when x is -4, the slope looks like it's about 2. When x is -2, the slope looks like it's about 0. When x is 0, the slope looks like it's about -1. When x is 2, the slope looks like it's about 0. And at the end, when x is 3.2 or almost 4, it's really hard to tell what that value actually is, we're saying that the slope is about 2. So what I'm going to do is I'm almost going to graph those as if they're actual ordered pairs, which they're not. We're sketching the graph of this derivative. So I'm going to graph the point -3.2-ish and +2, because when x looks like it's about -3.2, the slope looks like it's about 2. I'm going to graph that same point on the opposite side. When x is +3.2, it looks the same. Then our slopes looks like it's 0 at both positive and -2. And then our slope looks like it's -1. Looks like it's -1 when x is 0. So I'm going to sketch those points. And then now that I have these points, I can sketch a curve going through them. So this is an example of how to look at an original function, analyze the slope at different values to sketch the graph of the derivative. So this over here is our sketch of f prime. But what we need to think about is what happens if we actually have to work the opposite way? What happens if we're given the graph of the derivative and we need to look back and analyze the graph or create the graph of the original function? And before we go in depth in sort of these directions, I actually want to just remind us of some things that we should know based on previous units. So here are some tips, some tricks of the trade for you for looking at the graph of the derivative in an xy plane that may help you when you are sketching the graph of a function. So first of all, if you're looking at the derivative, where the derivative physically is in terms of the x-axis, if it's above or below, tells you if the function is increasing or decreasing. So if you look at our image over here, here and here in purple on both ends, the function is above the x-axis, or the derivative is above the x-axis. That means that our f, our original function, is increasing on those intervals. Similarly, between -2 on this graph and +4, all of those values are below, which means that our function f is decreasing on that interval. So by looking at the graph of the derivative and physically identifying when it's above the x-axis and when it's below the x-axis, that's going to tell you where your function is increasing or decreasing. The next thing we need to think about is those key values where that is actually changing. And this was a big topic in Unit 2 where we talked about relative maxes and mins. And that happens when our derivative is changing from positive to negative or from negative to positive. So remember, if we're changing from negative to positive, that means we have a local minimum, which would happen right over here. The derivative was negative, at 4 it's 0, and then after 4 it's positive. So we would have a local min because the derivative is changing from negative to positive. On the reverse side of that, we'll have a local max or a relative max when the derivative is changing from positive to negative. And that was a big topic in the last unit. So now you're going to be looking at the graph and seeing where is it crossing the axis. That's going to help me identify my relative extrema. The last thing to think about is we haven't really talked about the second derivative, but all of 3.1 focused on how the second derivative tells us the concavity. Well, the second derivative is just analyzing the slope of the first derivative. So if we're looking at the slope, we can identify the concavity as well. Meaning if the slope of our derivative is increasing, that part of the graph would be concave up. If the slope of our derivative graph is decreasing, that part of the graph would be concave down. So I just want you to really, this table is such a helpful little piece of information in terms of reminding you the different parts and how these graphs tie together. So let's go work through an example where we are given the first derivative and we're being asked to graph the original function. So here we are down here on this example. It says use the graph of f prime to sketch the graph of f with a starting point of 0, 1. So something to note is that if you are not given a starting point, your graph could be shifted vertically. If you are given a starting point, that just basically tells you that that is the only point you know for sure exists. So I know with absolute certainty that this graph goes through this point right here at 0, 1. Let's look at these little tips for helping us get started. Antiderivatives, or sort of the reverse of a derivative, the opposite of that, when we're going from the derivative graph to the graph of the original function. Something that might be helpful is to start by making an f prime number line using the location or position of points on the graph that we have. Now, this is not talking about the slope. The slope of a derivative graph is only going to tell us about the concavity. We'll use that actually in step 2. In step 1, we're looking at physically where is the graph above and below the axis. Number 2 says to make an f double prime number line. That's where we're going to analyze the slope. This tells us the concavity. Then we can combine those pieces of information together with a starting point, if we have one, to sketch the curve. And if we don't have a starting point, we have a little bit more freedom in the shift of where our graph actually goes. So let's look at this graph of the derivative. I'm going to start by looking at where the derivative graph is positive versus negative. So on this purple interval, which I did not trace very well, it's positive. So I'm going to go over here, I'm going to put 0 in the middle because that looks like where it's changing from positive to negative, and it's positive over here. And then I'm going to look everywhere. After that, it is negative. I'm going to note, let's just say this is negative 3.2 and positive 3.2 since this is not continuous. It's continuous along the closed interval, but it's not open. So we also just identified that our derivative is increasing and then decreasing. So we just actually found that we're going to have a relative max increasing to decreasing at 0, which makes sense. We have this point already plotted there. 0, 1 is going to be our relative max. Now we're going to look at the second derivative. When we're looking at the second derivative, we are going to analyze the behavior along the graph of the derivative. So I'm going to start by identifying points that I'm going to kind of look at. So I'm going to my ends are still going to be negative 3.2 and positive 3.2. It also looks like some interesting things are happening with the slope at positive and negative 2 and at 0. So I'm going to analyze the behavior between those numbers. So between negative 3.2 and negative 2, the slope looks like it's positive. It's definitely increasing there. Once it gets to -2, it looks like the slope starts decreasing. It continues decreasing after 0, but I can tell that 0 is going to be like there's something significant happening there. We're going to talk about that in a second. And between 2 and 3.2, it starts increasing again. So this is actually helping us identify the concavity. On the interval from -3.2 to -2 and from 2 to 3.2, this graph should be concave up. And from -2 to +2, it should be concave down. So we just identified concave up, concave down intervals. We identified that we had that relative max at 0 from our analyzing our first derivative, increasing, decreasing places. And then also the concavity is going to be changing along the way, and that's going to happen at any inflection point, which it looks like is happening at positive and -2 based on our second derivative sign chart. So it looks like right around positive and -2, and I'm not going to put points, like solid points there, but I'm going to kind of mark to myself at those values, it is going to be changing concavity. And now those points could be up a little higher. We don't actually have any idea where on the graph they are, but they could be up or down based on that. But once it crosses through x equals positive and -2, it should be changing from concave down to concave up. So it should be concave up on the edges. So this almost kind of is going to look like a quadratic, with the exception of here and here we're concave down. But as we continue going, it should shift to be concave up. So as we can continue going, it should shift to be concave up. So these are very rough sketches, but you're getting the idea that the first derivative is telling you where we're increasing and decreasing, and relative extrema. The second derivative is still telling us the concavity and inflection points, and that's going to help us when we are sketching those graphs. All right, we're going to do just one more example. Here we are given the graph of the first derivative, and we're going to be asked to graph not only the original function like we just did, but we're also going to be asked to graph the second derivative. Now, the relationship between these three graphs is really important, and there are some other videos that I'm attaching that I did not create that I'm going to attach in the video section on Google Classroom that really focus on kind of analyzing and comparing those three relationships. Also, I apologize, I don't know what these weird little lines that are going through this are, but I can't seem to get rid of them, so bear with me. So looking at f prime, the very first thing I want to do is I want to analyze the behavior. I want to look at where it's above and where it's below the x-axis. So it's above the x-axis everywhere from -2 on. So -2 is going to be that significant number on my number line. Everywhere after, it's positive. Everywhere before, it's negative. So we just identified a relative min at x equals -2. Relative min at x equals -2. We also identified that f is decreasing from -infinity to -2, and f is increasing from -2 up to infinity. So those are also important values to know. -2 is a key turning point where the graph goes from a negative slope into a positive slope. Now, let's make our second derivative number line. So I'm going to erase this red here. What we want to do for the second derivative is we want to analyze the slope of our first derivative graph. So the key number where the slope is very clearly changing is happening when x is equal to 0. Everywhere along this curve, the slope looks like it's just 1, up 1 over 1. So it's definitely positive. After it hits 0, the slope is also still positive, but it sort of looks like it's shifting. If I looked here, it looks like now it's more like 2. So down here it looked like it was 1. Now it's getting sharper. This spot at 0 also looks like a sharp turn, which means that the second derivative is not going to exist. So f double prime does not exist when x is equal to 0. So when anywhere that we have anything happening on our second derivative graph, we're going to need to have open circles at 0. So thinking about the left piece of the graph, I'm going to actually go back and use a different color. This piece has a constant slope happening basically all the negative numbers up to the axis, and that slope looks like it's 1. So how would I represent that as a graph? I would have a constant slope, so a y equals 1 line, basically from negative infinity up to 0, open circle. And then at 0, still an open circle, the slope seems to be changing, and it seems to be changing to go up to 2. So at 0, suddenly it looks like we're having a change in our slope up to 2. And something I'm going to try and make that look good. Something I want you to think about, that right portion of the graph over here, it kind of looks like x squared. And if you think about that and you differentiate that, that gives you the line to y equals 2x. So this sort of right portion piece does seem to make sense mathematically when we're thinking through what that would look like. So there's the graph of our second derivative. Now thinking about the graph of our original function, f, we now know that f, I'm going to add something to our list, we know that f is concave up everywhere. I guess I could just write concave up from negative infinity to infinity, because the second derivative is always positive. The slope of our graph of f prime is always positive, which means that this is concave up everywhere. We identified that we have a relative min at -2. We weren't given a starting point, so I could put that here, I could put it here. It doesn't really matter where I put it because this function could be shifted vertically based on any given starting point. So I'm just going to put it here. I know that there is a sharp turn in the derivative happening at x equals 2, but that's not a sharp turn in my original function. I'm sorry, when x equals 0. So really all I care about is that I have a graph that is concave up. It goes from decreasing to increasing at x equals -2. This is not a sharp turn happening when x equals 0 because there is a derivative value. The derivative exists when x equals 0. The second derivative doesn't, but the first derivative does. So that would be an example of a graph that we could graph here. It could also be shifted vertically. So just one last time looking at this sort of list of reminders, the first derivative, where it is above and below the axis, tells us where f is, our original function f is increasing or decreasing. Where it's changing sign tells us about our relative or local extrema. The slope of our derivative graph tells us about the concavity. So when you are looking at these things, you might find it helpful to sketch a number line for your derivative and your second derivative and combine those two pieces of information together to give a sketch of a graph. Looking forward to seeing you in class.